So I've shown you the call strings approach and how it's implemented. So basically pushing call frames onto the stack at a call and popping them off the stack at a return, and then also how to implement your merge operator. And this might look nice and simple, but there are actually some problems with this approach, also some very fundamental ones, I'm afraid. Um, and probably the most fundamental limitation, I would say, is really that the whole approach requires what in the literature is called k-limiting. So k here is some constant number k, typically also a very small constant, such as 0, 1, or 2. And yeah, actually, to guarantee termination of this whole approach, you can already imagine that you must limit the length of the context strings to a constant number k. Why is that? Like I explained to you previously, in the call strings approach, you're basically extending your abstract domain. So you're taking the original abstract domain for the context insensitive analysis and you're extending it with these calling context strings. But for recursive programs in particular, these strings can be indefinitely long, right? So you could recurse into calls forever, and these strings could grow indefinitely, and then you have an infinitely large abstract domain, and you already know that this is not okay. In particular, it's not okay if you have infinite ascending chains, and you would have these infinitely long ascending chains in your lattice if you were to do this, and then you lose this guarantee of termination, right? And actually, for all practical purposes, you would also lose termination. You would not just you'd lose the guarantee, you would definitely not get a terminating analysis. And even in situations where the analysis does terminate, for instance, because the program is not recursive, choosing a large k is typically not a good idea, because if you have too large k, then you can actually quickly lose performance. You can imagine a large k means that you're actually building up a very large number of calling context strings. So, if k would be 10 or so, let's say, then you could have n to the k different calling context strings, where n is the number of call sites in your program, and this can be a huge number. So you should not choose k too large. But unfortunately, if k is too small, then you lose precision. And so, for instance, in the limit, if k is 0, you end up having a regular context insensitive analysis again. So you basically you can just go without using call strings altogether. If you choose k equals 1, then you only have a single level of calling context strings. And that gives you some added precision, but not a lot. And the problem is then, because you lose some precision, right, or at least you don't gain as much as precision as you would like to gain, as a result, you might again lose performance. Why is that? Well, let's assume you're doing a taint analysis, for instance, okay, and now you're choosing a very small k. Then the problem is that you're still conflating calling contexts, right? So you're still propagating information back to return sites that are actually irrelevant, because normally looking at possible runtime traces, you would see that you're actually propagating it along unrealizable paths, what we actually wanted to avoid. But because we're doing this, we're propagating these taints or whatever analysis information into program places where it doesn't belong. And all of this is generating extra work. It's generating superfluous work, right? And that's why this can actually cause significant performance drops. So that's also very bad, right? So you get imprecision and you get bad performance. And choosing the right K, therefore, is really essential, but it's also not very easy. If you assume that you have chosen a K, which can be done, for instance, through different test runs of the analysis, some people even use machine learning to find the optimal K, then how do you actually deal with this? So let me show you how this works in principle. let's assume we have such a calling context string here attached to some data flow fact, and we have a bound k. Okay. Now here you can see that we have already k plus 1 frames, right? And let's assume that the bound k means that we want to stick with these k plus 1 frames, right? So the first one basically doesn't count. And now when we add another call frame to this, so for instance, we are now calling into a call site CA, and we would normally want to add this to the stack, then what we will do now is we only maintain suffixes of length k, okay? Or here it's actually k plus 1, but it doesn't really matter, right? So important is that you get the basic idea. So in this particular case here, we would be adding CA at the top of the stack like we usually do, but importantly, we would drop C0. Okay, so that would simply be dropped from the stack. And so this means now we will be propagating the data flow fact that has this call string annotated through the procedure that is called by CA. Okay. And then we will return it to after the call site CA, we will return it to after CK, and so on. But then once we return it back to after C1, when we then reach the next return statement, we don't know anymore where to return it to. Okay. So here we still knew that it needed to return to be returned to C0, or probably that would have been S main actually. But now we don't know that anymore. And then we basically need to return it again to any potential call site. So any call site that is present in the call graph, and that gives you again in precision. Now, the good thing is there are some worst case bounds. So k does not need to be arbitrarily long. So if capital K is the length of the longest non-recursive call sequence in your program, which can be very long. So for realistic programs these days that use frameworks and libraries, this can easily be 200 or so. And this value here is the height of the lattice, L. Okay. Then, assuming that you have a finite lattice with a finite height, the number of contexts can always be bounded by that number. But you can see, it's not exponential, so that's good. But it's already pretty large, right? So you have a k here, which is, this length of the longest non-recursive call sequence. That can be large. Your lattice can often be fairly high, depending on what you want to do. And if it is high, so if it's a non-trivial lattice, then this number is even squared, right? So you can end up having actually quite a large value. What is the intuitive explanation behind this equation here? Basically, you can have up to this number of values on either side of the staircase diagram, and all of the combinations are possible here. That's why this exponent 2 comes into play here. If you take a look back at these staircase diagrams, that might probably help you explain this. Now in 2008, these two colleagues here, they showed actually a better linear bound, so this can actually be lowered here in some cases, which is nice, but still this can be actually a fairly high number. And I would also say that this number here, it's a nice theoretical result, so you can bound it. And so what this basically means, if you choose a higher number, you don't lose any more, so that's actually good. But in practice, if you look at what people actually do, they will typically choose a value of k that equals 1 or 2. At the highest, I've seen something of 3 or 4. But typically anything more than that, it doesn't scale anymore anyways. So really, these equations here, I don't think they have much practical value, because in basically all the cases that I've seen in practice, you would choose a smaller k anyways. But this is, yeah, major practical limitations of the call strings approach. And it's particularly a limitation because there are so many call sites, and therefore this k can be quite large, right? And you can have very long sequences, and therefore, yeah, this can become quite unscalable. But there are other notions of context sensitivity that try to model contexts not really through call sites, but through other means. And that I want to talk about after the next break. And I think it's important to talk about this because using these other notions, you can basically get something that also feels a bit more natural to most static analysis, and also follows more the model of object-oriented programs and how they execute. And that's always a good thing, because I've also found in practice that if you have a program analysis that closely models the actual execution, and also an intuitive programmer understanding of that execution, then often it's a very reasonable analysis that will also give you good precision and speed. And these other notions of context sensitivity, they slowly bring us into that direction. So I'll see you after the next break.